This is our third session. It's just me tonight. Siobhan will be here next week. And we've got an interesting lineup for you, continuing our exploration of Java, but we're hoping to leave the core language behind now and start to take you into the world of some of the Java libraries. And after this week, we'll be pressing on with much of our core curriculum in agile techniques in general, starting with testing next week. Still need to cover some material though of the fundamentals, and this week our topic is inheritance and collections. With 4 talks in here to go through with you this evening. General introduction to inheritance and a specific type of inheritance called implementation inheritance. And then another variant of a similar concept called interface inheritance. These are 2 distinct variants of the same concept in Java. One of those is now considered to be flawed, and the other is considered to be the most appropriate type of deploying this concept in our software. So it's interface inheritance is where the sentiment is shifted dramatically. Once you've concluded that, we'll have the toolkit to look at collections. This is a very fundamental and important library that's part of the core JDK. It's quite a complex and large, sophisticated library, an award-winning library, in fact, in its time, perhaps showing a little bit of its age now, but still very much widely used. We introduce collections and review the primary features, and then we'll go through some more advanced topics in collections. It's too big a topic really for us to spend too much time on. We've one lab this week, as before, continuing with the little application you're building. This one is moving on a little bit further, and remember from our discussion last week, this is the foundation for your assignment. So perhaps at the end of this lab you'll be able to have a good go at the core features we've asked you to have a look at. There will be more to come in the labs for your assignment, but the substantial range of at least core features will be implemented by this particular week's lab. Okay, the chat room is here as usual. We are blessed with 3 chat rooms, not when 1 would do. So we have this chat room here, which is private. I may have emailed you asking you for your ID to invite you into that room. If you're not in the room, you could drop the email into the chat room on Adobe Connect here. And what I'm looking for is your Gitter ID, which might be your GitHub ID if you link your accounts. We can do that during the break. I'll be taking breaks as we go along. I realize that some of you may not have access to it yet, so I'll keep monitoring the Adobe Connect chat room as well currently. Okay, so we're going to start then with our introduction to inheritance. It's an interesting topic because of the way it has changed over the years from its original concept to now what's considered better or maybe less good practice. And we'll try and touch on that today, but we'll be doing more of that a bit later on as well. You'll recall we had quite a rush last week to get through the range of fundamentals of the language itself. That is, in last week's sessions, we were looking at overviewing the language, classes, control statements. And of course, we also spent some time exploring the assignment we've asked you to have a look at. This week's topic is here. We're looking at inheritance for the first few talks. And once that's out of the way, we can proceed then to look at collections. 2 fundamental parts of the Java ecosystem. Now, the other topics here we will be covering, but not today. You'll be glad to hear. Exceptions is a topic for a future class. Again, the way we use exceptions has changed over the years, so we'll be interested in looking there at how exceptions were originally designed and now how certain modes of using exceptions are considered poor practice. And we've already started a little bit on streams, but we'll do it in a bit more detail. That'll also be the next week or 2. You're using streams in the in the labs at the moment without any real explanation. I think we're going to fix that in the next few sessions. Okay, inheritance then itself, let's look at what it is, and then we'll focus our first talk on this specific type of inheritance called implementation inheritance. We look at the syntax in Java, look at some of the quirks, look at how it impacts on constructors, and then we'll also introduce the concept of abstract classes. There is another kind of inheritance that I'll be mentioning called interface inheritance. Both share general concepts, but their realization is quite different, and we need to be able to pull those apart in the next hour or so. Implementation inheritance is taught to promote reuse. Commonalities are stored in the base class, and we're sharing those commonalities across all the subclasses, and I'll explain those concepts in a moment. There is a fairly strong question mark now around the first of these. That is, does it really promote reuse in an effective mode or not? We will be discussing whether that really worked out or not in a later class. Interface inheritance is shifting our concept from classes to types, and we talk about whether a given class supports or implements a type rather than more general inheritance concepts. It's a subtle change of terminology and ultimately quite a significant change in how it's realized. Leave that for the moment, and let's just look at the concept. The concept is more generally called generalization and specialization. It's a core relationship that is perhaps part of the problem domain we're tackling, or visible in some analysis of the problem domain. And here we're seeing a policy, and then maybe a home policy, auto policy, and life policy. I think talking to some life people about policies is a bit risky, but we'll press on. The idea here is that at the base class, that is up at the higher level, there is a generalization. And this generalization represents an idealized or maybe abstract policy. And then we choose to introduce multiple realizations, and these are called specializations of that policy, as other classes in our implementation. And those classes inherit, or we could say share, aspects of the base class. Syntax is via the use of the word extends, which we append to the class declaration. And once we introduce that, we have to name the base class, and then we're introducing that relationship. We noted last week that Java is one of those languages that has a cosmic superclass we call it object. So if you introduce a class without any base class, it does already have one. It has object. So there's no escaping the inheritance relationship in the Java language, which is why we need to be very comfortable with how it works. When we introduce objects or variables of a given class, we often declare those variables to be associated with the base class rather than the derived class. For instance, in this line here, we're declaring a policy object to be of type policy, policy being our base class here. But we're creating an object that is an instance of the derived class. We're saying I want a life policy. That life policy is this class over here. And we're happy enough to do that. That is to generally tend to prefer our types associated with base classes rather than derived classes. We'll discuss why that is a little bit later on. Now, what do you get in inheritance? We can think of inheritance as a special type of relationship between two classes. In fact, it's a very closely coupled relationship. We're getting everything. We're getting all the fields and all the methods. The only thing we're not getting is the constructor, which we'll talk about in a second. So if the base class has a range of fields, those fields are now in the derived class objects. Similarly, any methods now become part of our derived class. Remember, we're introducing a new class. We bring in auto policy, life policy, and they will have all the fields we are declaring in the base class. So both methods and fields are inherited. and the inheritance hierarchies can be multiple levels deep. We're only showing one level here, but there is effectively no limit to how deep this inheritance hierarchy may go. Now, once we introduce the relationship, we do then have to consider things like what method is invoked, particularly if methods are shared between the base class and the derived class. So here is our policy again. We have a premium get premium method, and we're attempting to invoke that method inside the derived class. This triggers what's called method lookup, and in our derived class we do not have our own implementation of get premium. So get premium is going to have to be triggered from the base class. This means that the lookup takes place on the object itself, and we revert to a method one level up in the hierarchy when we wish to perform the get premium operation. This is possibly the source of some of the challenges to do with inheritance, as we'll see later on. We're not quite sure which method is being invoked, and we may end up going up and down hierarchies attempting to find the method that is most appropriate. Now, it's not obvious in this simple example here, but this proves to be a bit of a flaw in the design of inheritance, the flaw really being complexity. Here's another example. This time we've got a class called home policy extending policy, and we're invoking a print method. Now we're invoking that print method from within another version of the print in the derived class. So we're looking here at a print method. Its job is to print out the policy details, and we note we've got this funny syntax here, which is super.print. So super is a keyword only relevant when we're in an inheritance hierarchy, and in this case it triggers an invocation of a base class version of print rather than the current print. If we were to leave out that super, we'd be in trouble, because we'd be invoking print, and that would be a recursive call on print, which means our program would crash with a stack violation almost immediately. We can ask a class, what is our type? We rarely do this, but in certain circumstances we may be either confused or we may have a design that is overcomplicated, and that requires us to find out, well, what type are we at this point? This would occur when we have acquired access to an object without it being typed to its derived class. So it was an object class we were interacting with. We won't have cause to use this or really be seeing it again, but it's useful occasionally when you're exploring the concepts initially to try out these features, just to get a handle on the nature of typing in Java. You can invoke get class on an object, and then you can even ask it for its name, which will be the class name. Let's go back to our print example again. Here we're in the derived class print. We are invoking the print method. We're using the word super. So the super means we're going straight up here and we're invoking the print in the base class. That print method is printing out its own fields. We notice it's also taking advantage of the get class method to just flag what we think is the class name at this point. And when that's finished, we'll proceed with the derived class implementation, and ultimately the output will be a combined output of the base and the derived class print. Again, that looks a little bit complicated, and if you're finding it challenging, if you're new to Java, well, it's not surprising you're finding it complicated, because it is. And because it is complicated, we are shying away from this pattern in general. The print method is an example of overriding in Java. And when we say we're overriding, it means we're matching the base class function precisely. And then we are implementing that base class method with a revised implementation. We don't have to invoke the base class method in our derived class, so this is not required in any sense. It's just optimal in this particular environment here. Okay, constructors then are also implicated in how we implement inheritance correctly. If you've got our base class policy and a derived class home policy, and in this instance now we are initializing the base class with a range of important fields, then our derived class must provision those if we wish to have that constructor invoked. It's the same syntax we just looked at with print. That is, we have a super keyword, and that super keyword triggers the invocation of the base class constructor in this instance. We're not naming the constructor, we're just automatically selecting it based on its parameters. This is essential. If we don't match the base class constructor, we may get an error. If there is a zero argument constructor in the base class, then it works automatically and we don't need super. That's a subtle source of bugs there in its own right. Abstract classes. So we've looked at the basic concept, the extends keyword, the use of super. Super used both for overriding methods and for ensuring we can acquire the base class constructor invocation. Last topic in this section is abstract classes. And we have a new keyword in Java, the abstract keyword. We can denote a class to be abstract. This is a design decision we may take, perhaps based on the problem we're solving. Perhaps we're capturing a concept in our class that we never want to be concrete, but it does lay down the shape of something that's important, and perhaps that will share a behavior and a structure across multiple classes. So a generalized policy could be marked abstract. We may never, in fact, we may insist upon never implementing a policy. And then we're free in our derived classes to implement the policy completely. And the abstract keyword marks that we've made this decision. In addition to marking a class abstract, we also can mark a method abstract. And this gives us even more detailed design information. We're saying that this class is not only there and perhaps has certain fields, it has specific methods which must be implemented for a concrete class to become viable. Note here that I have a semicolon there. That's important. There's no body or implementation to this class. This class has no meaning in policy except that it is defined. That is, its signature is established. So it's an abstract method, and then that abstract method must be implemented in the derived classes. If those derived classes do not implement a method, then our Java environment will object. It won't object unless we attempt to create an object of the derived class. So we may choose to not implement calculate full premium, but in that case, we're still living with an abstract class at that point, and a further derivation step will be needed to make it concrete. Okay, that's a basic roundup of implementation inheritance. It's the extends keyword. There's overriding. There's the use of super to trigger base class methods or constructors. And then there's the added complexity of abstraction being imposed on the classes, whereby we can mark individual elements to be abstract, or we can mark the entire class as abstract, or both, as it turns out. I should mention that abstract classes may also complete function implementations, methods, and may also have their own fields. Now, one last topic, multiple inheritance. We can visualize B and C derived from A, so it could be home policy and life policy derived from policy. But could we envisage a D? Could it be a special hybrid policy of some kind, for instance, that was both a home and a motor, for instance? Well, that's not supported in Java, and I'd like to review very briefly why that's not the case. So a thought experiment, suppose we have a brace class, maybe we mark it as abstract, and we have a method do, and then we've got an implementation, implementing do, and another implementation, that is another class, also implementing the same method. So we're implementing the abstract base class in two concrete implementations. This is okay, that's perfectly fine. If we had multiple inheritance, we could be tempted to try and write a syntax something like this here. That is, there are two base classes specified in sequence. Syntactically, that might make sense. We might even imagine that it could be realized in some successful manner. And it could, but it leads to a breakdown in our understanding of overriding here. And because we've got a do method implemented in the base class, in the two derived classes, and now in the multiply derived class, then we have a conflict around which version of the do method should be selected. So when we invoke do on a diamond effect object, there's an ambiguity here. Now, addressing that ambiguity, we could envisage a syntax to resolve it. Java decided not to bring in such syntax, so multiple inheritance is not possible. It should be noted, however, that it is possible in a whole range of other languages, including the direct ancestor of Java called C++, and it uses a special mechanism called virtual base classes for just this purpose. That's it then for this topic for the moment. We've got our basic introduction. We will be returning to this type of inheritance a little bit later on in the module, but we'll take a short break now, and then when we resume, we will continue our discussion of inheritance, this time a different style. Let's take 5 minutes, and I'll be monitoring the chat room in that time if anybody has any questions, or you'll have a few minutes to take a little bit of walk around if you like as well. Okay, see you in a second. Okay, that's our little break over. We'll take a little longer one next time. Just 5 minutes is enough for now. So we'll keep the momentum going on this topic. Second part of inheritance, interface inheritance. So we've looked at the extends keyword, use of super and abstract, the three reserved words that define the use of implementation inheritance. Now we need some other keywords here to explore a different concept. Interface inheritance, we talk in terms of types and subtyping rather than classes and base classes. The terminology is not terribly important, but it is a subtle shift, and it is more in line with current thinking to use this phraseology rather than to rely on the older terms. Still the same concept as such. We still talk about generalization and specialization, but we realize it quite differently. So let's look at a definition, particularly what interfaces are, how it's implemented, some discussion on typecasting, which is relevant to both, in fact, and then some naming conventions. And then we're kind of in a good position now to move on. We're comfortable, hopefully, with the idea of a class at this point. Class has attributes and behaviors. That is, it has methods and also fields, as we've been implementing them. Java also has, as a first class representative in the language, a companion to classes called interfaces. Interfaces are superficially resembling classes, but substantially different. Interfaces contain largely only methods, and those methods are abstract. They're signatures, not implementations. They can't contain, in general, fields or attributes, and nor can they contain, in general, constructors. So they're close in concept to abstract classes with all abstract methods. Now, this has become blurred a little in more recent versions of Java. So Java 8 and 9 have finessed this concept a bit, and Siobhan will be taking you through that a bit later. So we'll keep it simple for the moment and assume it's the earlier definition. Here's an example of an interface. It looks like a class, except we don't have the keyword class initially. We just have the word interface. That replaces where we would normally put the class keyword. And also note that we're not using the word abstract anywhere, but we are terminating each method with a semicolon, like an abstract class. And there are no implementations of those methods in the class definition. So we say in computer science terms, this is a type. It represents a concept that has behavior, but not representation. I can do things with this, but I can't open it up and look inside it because it has no embodiment. Classes are used then to implement interfaces. So we're looking at the class address book. Instead of using the extends keyword, it's using the implements keyword. And this is establishing, we could say, an inheritance relationship to address book, but we think more in terms of a subtyping relationship, to use a more convenient terminology. And what that means is that this address book class must implement all of the methods defined in the interface it is intending to implement. It must, if you like, fulfill a contract here and fully realize these signatures. So we say the classes are subtypes of the interface, and the compiler will insist on that implementation being realized. We don't have a choice about picking and choosing which methods we implement. They must all be implemented. In fact, we kind of regard it as a contract. We are adhering strictly to a contract laid out in an interface. And we are, if our program compiles successfully, will have guaranteed to implement the interface. We do also have the ability to implement multiple interfaces. So the relationship we explored in the closing of the previous session, whereby we had a desire for a class to implement two other classes, well, we can approximate this here now with interface inheritance. And it's not uncommon for classes to implement more than one interface where it's appropriate. In example, car, a color, a colored car. And here we notice we're using the extends keyword. It looks a little bit odd, but we're in the interface world here, so it's reasonable for us to extend other interfaces and multiple interfaces if necessary. So we're not saying implements here, we're saying extends. Any class now that realizes colored car will be implementing those two interfaces as expected. We'll be looking at the collections framework very shortly, and here understanding of interfaces is quite important. You've already been using array lists in your labs, your little projects. In fact, you may also have explored very briefly a linked list. These are two classes in the collections framework, and both of those classes implement independently an interface. And that interface, that instance, is the list interface we'll be looking at shortly. When you introduce a variable, you may choose to associate the type of the variable with the base class, with the interface or the base class. So here is a product object. It's declared to be ostensibly an interface, but we realize it by selecting a concrete or implementation class, that is the array list. And this type of pattern would be quite common in your labs to date and in much of the code we implement. We'll return to exactly this concept shortly again. Now, most statically or strongly typed languages do have a typecasting facility, and we use this to override the language's default typing behavior when we are certain that we know a specific type is available, but hidden in the context of the current class structures. When we create objects, we can choose to associate the objects with the base type, as we're doing here. And similarly, with our address book example, we're associating the book class with an interface, the interface being iAddressBook we just looked at. So both of these examples, one using implementation inheritance, the other using interface inheritance, the objects we're using, policy and book, are typed to the base, not the derived. Now what that means is that for interfaces in particular, we will not be able to access any concrete methods unless they are defined in the base class. So if I apparently want to make an attempt to call a method locateIndex on the book object, unless locateIndex is defined in the iAddressBook interface, this is a compiler error. It's a syntax error. Normally, we're happy for that error to be detected. It means we've misconstrued our logic in some way. However, there is a way around it. And this is the typecasting syntax you may see occasionally in Java code. If we know the object refers to a concrete implementation, we can force the compiler to override its reservations and invoke, in this case, the concrete method. And this is the syntax we're using here to do that. We're saying, I know it's a book, force it to be an address book object, and then now invoke the locate index method on that for me. Not very attractive code. If we saw a lot of that occurring, we'd be raising some questions as to whether we were using either inheritance or interfaces appropriately. And we might be considering a reassessment. However, in certain circumstances, it's unavoidable, particularly when you're dealing with large and sophisticated Java frameworks. It's quite common in the Android frameworks, for instance, for you to use this type of syntax occasionally when you're interacting with Android framework objects in certain contexts. These are common naming conventions. There's no real set standard in this area, and in fact the JDK itself has a couple of different variants on this. We will, though, or we have seen a serializable already. Serializable is an interface defined in the JDK. It's a curious interface in that it has no methods. It's sometimes called a marker interface. So it's merely saying I have a type, but I'm not actually committing to any signature for that type. These other ones are also visible. Clonable does have some methods, and transferable, I think, is in some frameworks. I don't think it's in the base class SDK. Another style of naming these interfaces is to use the I in front of the name, I color, I car, I colored car, etc., and then remove the I for implementations. And yet another style is to use standard names for the base types and use impl for the implementations. That was a style very common in earlier distributed systems. No hard and fast rules, really. They're just common naming conventions we encounter occasionally as we're encountering legacy code or particular usage patterns in individual frameworks. That's interface inheritance. Core idea really around interface inheritance is that we are defining not classes but interfaces, and when we define those interfaces we are defining effectively a type, and that type then must be fully realized by any classes that choose to adopt or implement that interface. Implementation inheritance has some similarities, but the starting point is existing classes, and these classes may be partially or even completely implemented. And then inheritance in that context is augmenting or maybe overriding the implementation. I've mentioned at the start that their sentiment has swung quite strongly away now from implementation inheritance to such an extent that some modern languages no longer support it. However, they do support interface inheritance. A good example of that would be Go, the new language from Google. It closely tracks Java in many respects, but completely drops the former type of inheritance and relies exclusively on the latter in that instance. Okay, taking our short break, and our next topic we're going to be looking in detail now at what we can do with inheritance, in particular how inheritance allows us to build and use the very powerful collection frameworks. So I'll give you 10 minutes if you don't mind. I'll attend the chat room if anybody has any issues, and we will resume in 10 minutes time. I'll disconnect my mic. So we've covered, I think, in our last session and in this session, probably 80% of the programming language Java visited at some point or other. It's quite a breakneck pace, but it's also an indication of the reasonably tidy nature of Java itself. It's not specifically large language at its core. It's a simplification of its ancestor languages. So, for instance, C++ is considerably more complex. And even some derived or related languages have gone quite a good bit further in terms of their expansion. Thinking of JavaScript in particular, which is now much larger really in scope and complexity than Java itself. So if Java is first contact with you and you're finding it a little bit challenging, well, there's not an awful lot more really. And revisiting the lectures from this week and last week again might get you onto a reasonable footing for the remainder of the course. Of course, in languages like this, it's no longer the core language itself that is the challenge, it's the libraries, and particularly the libraries and frameworks we may be using for specialized application development. And it's one of those libraries we're turning our attention to now, which is the collections framework. It's part of the core JDK. It's a standalone library, but it's bundled with all Java environments. So, and it's heavily used by many of the frameworks that we use for specialized development in Java itself. So let's take a look at the collections framework. It's quite complex. We don't need to go in tremendous depth into the framework, but there is a range of core features you do need to be comfortable with. You're already using them in the labs to date, but we haven't really explained them in any sense, at least not yet. We're in a position now, though, to have a crack at it, particularly as we've got inheritance and interfaces under our belt, and hopefully it'll start to make some of what you've been doing a little bit more concrete. So the collections framework itself, well, it's effectively a library of data structures. Anybody who's come through standard computer science education will have covered data structures at some point in their undergraduate careers, learning how to build lists and sort arrays, binary trees, B trees, maps, hash maps, and a range of algorithms associated with managing those data structures. Well, they're fun to do, but often challenging to implement and specialized. And most programming languages we would expect now to implement good quality realization of these data structures. In Java, it's called a collections framework. So we don't attempt to build our own data structures really in production. We tend to rely on proven implementations for reuse, obviously. Uniform approach to these containers. Obviously, it boosts our productivity because we're not implementing core algorithms, and we're getting interoperability. We are interacting with other frameworks and libraries that are also built on these concepts. That's a bit of an eyesore, or an eyeful, should I say. That is a small snapshot of the current collection framework. In fact, I'm hiding a lot of classes and interfaces that are not visible here. We don't need to grapple with this or at this level. We need to look at considerably simplified vision of what the collections framework contains, and then build on that simplification to extend our knowledge just in sufficient areas to allow us to do some work. At its core, the collections framework is a set of interfaces, a set of implementations, and also a set of algorithms. Interfaces are, using the syntax we just explored, they are contracts or types that define a range of signatures. Implementations are classes that implement these interfaces. And there are also uses of implementation inheritance to further customize those implementations. The algorithms are usually bound into the classes that implement the interfaces, but there are also some general purpose classes collecting a variety of other algorithms that can be applied to different collections. The diagram we are most interested in, though, is this one here. And if we get this, then we're in business. There is an interface called collection and an interface called map and an interface called iterator. Almost all collections have a relationship with one or more of these interfaces. And the two primary ones, the ones in fact you've been using, well, you've used one of them, are also interfaces, the interface set and list. So if we want to get an understanding of collections, we need to tour these 5 interfaces first. And once we've got a basic understanding of those, then the implementations of these interfaces, the classes, should make more sense. So we'll start with a collection. Collection is a real abstract concept of what a collection of objects should be. It's an interface, so it's entirely abstract. There's no implementation, and it's quite a generalized view of what a container should operate, what behavior a container should offer, rather. So, for instance, the interface collection has an add method, allowing you to add some object to the collection, and it has an add all method, which will add every element in another collection to the collection you invoke this method against. So the core features of a collection is that you can add stuff to it, and that stuff will be retained. You can also remove. So once you put it in, you can take it back out again. And if you put in a collection, you may remove everything from another collection if it is still in the collection that you inserted into. Other methods in collection, you can check to see if an object is in there. You can check to see if a set of objects or a collection is in there. You can find out how big the collection is. You can see if it's empty or not. You can clear out the collection, or you can clear out everything except those that are members of another collection. And lastly, you can ask a collection for an iterator. And this is a way in which we can traverse the collection. It's a pattern, a fairly venerable pattern now in computer science at this stage. This iterator is a separate interface, and if somehow you can acquire an iterator, you can invoke methods on the iterator to move around inside the collection. So typically you might be calling next, but you may also call hasNext to see if there is a next available. And when you're traversing iterators, you're often working with these two in tandem to guide your algorithm as it's proceeding, say, sequentially from one object to another inside the collection. Set, well, set extends as it is derived from collection, so it customizes the collection in some manner, and it obeys the rules of algebraic set. Set is a collection that can contain duplicates. Otherwise, all the other methods work as you would expect, but if you insert more than one method, more than one object twice, then you can expect only one copy of the object to be inserted. List doesn't have that restriction. You can have many duplicates and they'll all be individual separate objects. List also has the concept of positional access, so you can get the first, second, third, or last element. Set is not equipped with that capability. So you have a range view possible in a list. And list obviously leads on to what you've already used, which is an array list in your labs to date. Map is separate from collection, and we can see it's related to a collection in some unspecified way here, but map is effectively a dictionary, name-value pairs. You put something in, but you're not putting it in to the end or maybe as a unique element in the collection. you're putting it in at a given key position. So it's a key value store, effectively. Now, they are only interfaces. They're not implemented because interfaces are abstract unless you specifically choose a class that implements them. And the three primary classes that are most often used in collections framework would be hash map, which realizes a map. Array list, you've already seen this in action. It gives you a simple container for objects that realizes list semantics. And set, or hash set in this instance, which is a container for unique objects. And there are the three building blocks really that you can start to extrapolate most of the collections in that larger diagram I showed you earlier are derived or related to these in some sense. So a few examples. Array list, you've seen this in action. You can create an array list, add elements to it, find out what size it is, and at the bottom left here, iterate through the list, that is, visit each element, selecting or printing out each element in the list itself. You will notice here I'm doing something we thought we'd avoid, which is casting. So every time I proceed through the iterator, I'm casting the next object down to a string, because a string is what I originally inserted up here. And we'll see in a moment how we can make this code easier to read and more elegant by eliminating the need for casting. We'll park that notion for a second. A list then is quite intuitive. Put things in, get things out at specific indexes, if we like. And of course, then we can find out how many elements are in the array, and we can clear it and so on. Hash map, a little bit different. It's where we're inserting at a given key value pair. Ordering isn't critical. There's a more complicated data structure, and there are some more sophisticated ways of tuning the data structure for performance. If you've ever studied maps in data structures, then there are obscure features around called load factors to determine how efficient the map is. It's not really our concern for the moment. We're just going to try and use it. And here's some examples. A dictionary, and instead of using the add method, we're using put, and in put we are specifying the key and then the value. And then if we wish to access an element, we're using get. So here we're doing key value insertion. We're doing a traversal. The traversal looks kind of complicated here. We're extracting an iterator, calling next, and then we're extracting keys and values. Again, we'll be trying to simplify this, and in the next slide deck we will be attempting to explore how we don't need this typecasting here, which is a little bit worrying. Set realizes the set abstraction. It's closer to a list in a map. We're inserting things into the list. So we've got the same method, in fact, add. We don't really, though, have the notion of an iterator to march through the set. And if we insert the same element twice, then it won't be inserted. There'll be no duplicates permitted, and one will remain. So back to our forest picture, we can see the classes we've been touring here. That's our collection interface. It's in dotted notation. This is the list and the set we were mentioning. And then there's hash set, which we've looked at. And the one you've been using is array list here. I think in the first lab, we invited you just to take a peek at linked list and see if you could change to using a linked list instead of an array list, just for as an experiment. Now, how do you know which one to pick? Which one do you choose? Which one is most appropriate? We're presented with a myriad, apparently, of options here. Well, choice between map and collection is clear enough. Map gives you keyed access. If you don't want keyed access, collection is fine. Distinction between list and set is also pretty clear. If you don't care about how they're ordered inside the collection and you don't want duplicates, set is simpler and more matches closely your problem area. If you do want sequence, you want a first and a last, and you want to know where it is in the list, then you're looking at the list. Now, list, however, has multiple implementations, not more so than the ones I'm showing here. And choosing to select which one depends on the nature of your usage pattern and the desired performance you're willing to suffer. It centers around how often you're updating, whether it's left or right only, whether you're updating the list in the middle, at the end, or at the start, and various other potential patterns. We'll take a peek at those a little bit later on. However, this is all we need really for our purposes, and certainly for our module, we'll hardly venture beyond these ones here. That is, we hardly venture beyond the core hash set, array list, and hash map. Now, there is one exception to that. We may be interested in a little bit later on, either be independently or perhaps under our guidance when we look at some other examples later, some related interfaces in the framework around sorting and searching. And these interfaces, comparator and comparable, can be quite important. They're not a topic for today, though. Our topic for today is just to get an introduction to the fundamentals, and these are the fundamentals here. These core set of interfaces and classes. You're already using them. You're using ArrayList already, and I think you're seeing they're reasonably straightforward to use. Okay, I'll take another short little break, and then just 5 minutes this time, and then we'll get into our last session, which is a little bit more complicated, but we'll explore it in any sense. Okay, so I'll see you in 5 minutes, let's say. Okay, I'm back again now. Good question there from Kevin. Question is, if the ArrayList class implements iterator interface, why do we need to get the iterator? That is, why do we need to type list.iterator? It's a good point. When we say the ArrayList implements the iterator, I should perhaps rather say that it exposes an iterator or makes one available. It doesn't actually implement the iterator interface. So when we say list.iterator, we're retrieving an iterator from the ArrayList, and then we're using it independently. That's kind of core to how the iterator pattern works. It separates out the iterator from the core data structure itself. We can discuss that more in the chat room at the end of this session, if you like. So we've been on a journey now from exploring inheritance, distinguishing between implementation, interface inheritance. And then we've encountered our first real-life example of that, perhaps in the collections framework, which is a range of interfaces and their implementations, and also some further implementation inheritance customizations of those classes, as in the linked and linked list implementations and others we will allude to briefly. Let's keep going with collections because we haven't got the full story yet. In particular, we need to talk about generic collections, the collection interface itself. We'll just have a quick look back at it to see if we missed anything. Some aspects around the features of collections and a peek at how you might reason with choosing a collection. And then lastly, just some observations on working with collections and some further references I'd like to discuss briefly. First of all, back to this examples that we had earlier, this number dictionary we had. And in this example, we are looking up the dictionary. Here, we're performing a get. The get is giving us back an object. That object is the value in the collection at the key 1. It is actually a string, so we're casting it then. And the cast operation is needed for us to actually recover the string itself. Otherwise, we just have an object that we retrieved. Now, this clearly isn't a very attractive way of programming. It was how collections worked for 10 years, a little more, 11, I think. But there was a substantial revision to collections made in about 2 releases ago of Java, and generic collections were introduced. And this allowed us to really have a closer look at the type system in Java and provide some amendments to that type system to improve its readability and reliability. And this came to be known as the transition from unsafe to safe, or from untyped to typed, particularly in collections, but the notion also applies to any other class that you would choose to build yourself. So once safe or typed collections were introduced, we had a significant reduction in the noise around using collections in terms of the syntactic signals we had to send. Simple enough idea, really. And again, you've already seen it. For declaring an array list, we specify in the array list the type we want the collection to manage. That's specified in angle brackets like this. And in between the angle brackets is a type name. And this can be any appropriate Java type. When we create an object that's an instance of a collection, we're then specifying the type itself here. The same type appears. This is called a parameter or a parameterized type. That allows us to drastically simplify accessing collections. If we go back here and look at some of the examples we had earlier, an array list, I can add things in the untyped unsafe or typed safe mode. And the key change here you'll notice is there's no cast required anymore here. When I call get, I'm getting back a string. This is relying on the generic features introduced into Java at this time. Same for iteration. If you looked carefully at the previous examples, there was typecasting required for the iterations to work correctly. Now it's no longer needed. Here I'm asking the list for its iterator. I'm using hasNext and next to guide me through the collection. And the next method in particular returns the appropriate object for me, a string object, which I'm printing out in this instance. So all of that is a big advance over what we had previously, and it's the standard way now we program collections. Particularly noticeable when we're using hash maps, because they can get very noisy, particularly all the typecasting. And the hash map as implemented now is easier to reason with. Here I'm declaring number dictionary, putting elements in, putting 1 in at position number 1, and then I'm retrieving the collection, the element here by key, without any casting required. For loop also introduced around this time, and the for loop works with iterators and then works with collections that the iterators are associated with. Sometimes called a for each loop, and there are variants of this now in most modern programming languages. So for the iterating through a list, we can dramatically simplify it. Here we have the version we encountered previously, which was using the iterator to extract a, if you like, a pointer or reference into the list, and then use that reference to guide us through a for loop and retrieve individual elements. Down here we have exactly the same operation using a for each loop. I just declare an element object, colon list, list being the array I want to iterate through, and this loop now will kick off for us. Every element will be visited, and I'm just printing it out. I don't need to explicitly retrieve the elements or automatically retrieved for me. Now it's important to note that this relies on and uses iterators, the for each loop. Unless your container supports iterators, the for each loop is not usable. It also means that the for each loop can be used in other contexts. You could write your own classes that expose iterators, and the for each loop would work with those. So it's a general purpose facility, not just bound to the collections framework. Let's look at the collection interface again, and another view. This is a little bit richer now than the previous one we had. We see we've got sorted and navigable sets here. We also have a queue and a deck. Again, these are variants of important data structures you may have encountered in the past. And also you notice we've got maps that could be sorted or navigable. So the names here are suggesting perhaps greater utility for some of these instances of the collections that may suit particular problems you're tackling. The collection interface itself, we've already looked at it. It's up at the base class. Let's just take a look at the other stuff that's in there. Add all, clear, contains, hash code, empty, iterator. We've just been discussing iterator in some detail. It's the signature there for the iterator method. Remove all, retain all, size, to array. These two actually are interesting. Didn't discuss these already. We can ask a collection to turn itself into an array. And you notice the bottom one here is a typed array. So possible to see how we could write some very simple and elegant code to interchange or translate from one data structure to another. Also note that the add all method, the signature, looks a little bit different now from what we had previously. In modern Java, we have generics, And where we have generics, we are passing types or indicating types in somewhat more obscure ways than we've been doing to date. A lot of controversy in Java around this question mark symbol here and what exactly it means. Don't propose to go into it now, other than to indicate that its meaning is highly ambiguous, and it's a bit of a problem for the language currently. Okay, quick tour of some other features. Performance, I'll name check, just to give you some references really for further reading. I'm not going to plunge into any detail. Here is just a kind of a summary table of some of the collections we've encountered and others you might want to explore. We're indicating here whether list, set, or map, the core interfaces we've discussed already, whether they're ordered or not, whether they're sorted or can be sorted easily, and whether they allow duplicates. So you might review that in your own time. Here's an extract from some analysis done on collections, and these are performance times in milliseconds or nanoseconds, sorry, for various types of operations on collections, and it's comparing different implementations. By the way, it's including in this comparison collection implementations that are not in standard library. So there are other collection implementations out there that have different performance profiles. Now, the nature of these differences adheres to the structure of the data structure itself. For instance, contrasting linked list with a non-linked or a standard array list. They have different performance profiles depending on how you're using them, whether you're inserting in the middle or at the start or the end, whether you're inserting and removing or inserting only, or other types of profiles. And the collections then exhibit different performance characteristics based on that type of usage. It's not really something we'll be getting into, that is algorithmic analysis, so much in our module. We're sticking with vanilla implementations and we're not really doing any profiling. But these profiling tools that we're showing here do indicate predictable differences in the performance for different types of operations across these collections. If you are using Eclipse and you are perhaps not adhering closely to generic or typed collections, then you do get a range of prompts from Eclipse to encourage you to insert your types effectively. So the compiler these days now are encouraging and almost forcing you into using proper generic syntax, and they'll fix the syntax if you're a little bit tardy in implementing it correctly. Also, they've been tuning the way some of these work lately. In particular, in the earlier example, we had a hash map. You may have seen hash map string string with string string appearing twice in the declaration. Well, this has been cleaned up in version 8, I think, of the language. So here we're seeing it's possible for us to have a slightly more elegant version of the declaration with just a single occurrence of the hash map string string syntax. Sorry, I'll clarify. I'm talking really about how this here has simplified our life slightly. Now that's an example of a little bit of type inference. We mentioned this in the very opening talk. That is where the compiler intervenes and figures out that it knows what you're doing and not so much inserts the type for you, but assumes the type is there and doesn't cause any objections subsequently. So for instance, we have a choice here of whether we insert string comma string in here again or not. And in this example, we're choosing to not do it, and we're not going to get any warnings or complaints. When we're using collections, just as we looked at earlier on in the inheritance talk, we generally tend to type our collection instances to the base type if possible. So the products is an array list, but I'm choosing to select list as the type of the products instance. Similarly, a map in that instance, or a set. Now the reason we do that is fairly simple really. It allows us a little bit more flexibility in our implementation. It means that depending on the performance profile of our application, perhaps depending on results we get from running a profiler and looking in real life at how our data structures are being used by user data, we may change the implementation from linked list to array list, or array list to linked list, for instance. If we have typed the instances to the base type, we can do this without penalty, without further compilation, without further syntax adjustments. It becomes immediate and painless. In other words, we can refactor along the inheritance chain for a given data structure easily and without it having a ripple effect throughout our code. We've been using this in the few labs we've done to date. We've generally been attempting to declare lists as opposed to array lists, even though array list has been the concrete type. The for each loop, we've seen that again. Just refreshing your memory on it. They rely on the iterator being available, but we get substantial reduction in code size. 2-3 statements reduced here in this instance, which is quite attractive. Okay, that's more or less it then for our review today. Back to the diagram we had in the last talk. These are the main ones we're interested in for the moment, really. We realize we've got iterator, collection, map, set, and list, and then the 3 implementations we're happy enough to run with. We are able to use generics now across all of these as opposed to the legacy implementation. And we also have a for each loop now, which makes the traversal significantly simpler. There are a full range of other data structures I haven't explored here yet. I'm just mentioning decks here, tree sets, linked hash sets, and so on. Some summaries to why you might select those. For our module, we're happy enough to stick with the vanilla ones, so it's fine for the moment that we stick with our core. It is worth mentioning that there's a whole other family of collections out here, which is a little bit unnerving when you encounter it first. That is, the collection library has been dramatically expanded to cope with multi-threaded applications. So for all of our base interfaces, set, list, and also queues we didn't mention, there are concurrent variants of these data structures. Now we won't be doing any concurrent development. And multi-threaded development like this that would use these collections is quite rare and very specialized. Even in concurrent applications you may be building, Spring or other web applications, generally concurrency is excluded from the remit of the programmer, and you're relying on other abstractions internally to shield you from multiple thread access. However, they're all there. They're quite well respected, very complex, and quite an engineering achievement. Just mention some references. The most referenced book on modern Java development is probably this one here. This is only ever went to a 2nd edition, and I think that was about 7 or 8 years ago, so it's due an upgrade, but the author doesn't show any signs of producing one yet anyway. The author is a very well-known figure in the Java world as the primary architect of the collections hierarchy we've just been discussing. He worked at Sun at the time, then at Oracle. He now works at Google, I think. He has moved on to other languages since. I think that's why the language itself, the Effective Java book, has not been updated. I mentioned the question mark we spotted earlier on there in the collection interface. He has famously indicated that he no longer understands what that question mark means now. And he was closely involved in the design of the generics feature and its realization when he was working at Sun. So it's a little bit worrying that there are some loose ends there, but we'll glide over that. These two books I think are really excellent. I think if you're becoming a Java specialist, there's nothing like a book, and the Good Parts book is really excellent and well worth reading. Nice thing about it is it's 150 pages, not 500 pages of stuff. So well worth a little investment if you're interested in getting on top of this field. You don't need it for this course, really. Jim Waldo, again, is another very well-known veteran in this field. He was a veteran of the C++ days and did a fine job on that book. If generics and collections are really interesting for you, we do have another text. It's a bit more substantial than this one. I haven't read it all, in fact. It's useful enough, worth perusing perhaps for reference purposes. But generics have become a little bit tainted now, so investing heavily in trying to understand them when they're a little bit broken is well, it's a little bit off-putting perhaps. I could recommend the Good Parts though, and the Good Parts series in general is well worth checking out from O'Reilly. They do the Good Parts on quite a range of languages and frameworks, largely because these languages and frameworks have changed over time and accrued a lot of cruft. Java, perhaps as much as any other language. So the Good Parts attempts to distill down the subset that's modern and useful, and gives you some indicators and pointers as to which parts of the language are best avoided. It's particularly good on indicating which parts of the JDK and framework classes are best avoided, because there is some quite dated approaches in there which have been carried around now for many years, and sometimes the wisdom gets a little bit lost as to what you should avoid and what you should take seriously. Okay, that's our finishes our session for today. Thanks for your attention. I'm going to hang around in the chat rooms until 7 or 20 minutes. Labs go live tomorrow in the chat rooms again from 3 to 5 IST hours time. So we'll be attending those labs and happy to help out if you're having any challenges there. Next week, Siobhan will be back, and we're moving beyond our review of Java now at this point, and we're moving into some core practices of agile development, specifically testing. But we will be dropping in on some Java features occasionally just to tune up our knowledge and keep an eye on some recent developments. Siobhan is looking forward to taking you through some Java 7 and 8 features, maybe even some Java 9 features, although they're not quite released yet. Thanks again for your attention. I'll be putting these recordings up as soon as I can, hopefully tomorrow at some point, and I'll be dropping in you next week as well. Thanks again, and see you soon.